Right. Good afternoon, everyone. So we'll get started. Switch this over. Okay. So lecture 13. So as a quick refresher, last class we talked about kind of the evolution of how you go from these linear models to thinking about more semi-parametric or non-parametric approaches, right? So where we went from linear going to polynomial or stepwise, and then how these guys end up contributing to how we think about doing splines. And we talked about normally the form of this is through a cubic spline. We showed the progression to natural splines. And then I believe the last thing we talked about was smoothing splines, right? Okay. And so remember that the concept behind these approaches is fairly kind of ingrained in thinking about things from a predictive sense, or at least that's kind of how it's originally devised, right? As opposed to inference. These don't have like coefficients or anything that we can easily interpret, but they do give us a lot more flexibility to be able to predict non-linear outcomes, right? And so the real strength of these approaches is its application to non-linear functional forms, which your traditional sort of linear models might have a harder time dealing with. But I actually want to show a common example of applications for splines where we actually pull back into the sort of inference space or depart a little bit from prediction, okay? And so this is kind of like a hybrid thinking where we can have something to say about how an individual variable may relate to an outcome, but maintain a little bit of interpretability in the same vein as inference is trying to do. Yeah?
When you say parametric, are you referring to the coefficients for the linear model?
Yes, correct. Yeah. And so when we talk about like semi-parametric or non-parametric, you're talking about now either not really having coefficients that we can really interpret, or coefficients that are connected to transform data that is also not very easy to interpret. So when you think about like the squiggliness of a spline, you have coefficients that are associated with the basis functions that transform the data, but they don't really mean anything interpretable. Yeah. Even even when I'm kind of joking around about like in discrete choice models and like logistic regressions, where I'm like, well, those coefficients aren't like so interpretable in the like quantitative sense where I could say some change in X leads to a particular change in Y. That's not totally true. There's something to be said about the magnitude of the coefficient and its sign, and so there's still some interpretability there.
Parameters to kind of apply across the whole range of input values.
Yeah, exactly.
Splines going with small.
Yeah, with splines, you really can't say anything about the outcome as it relates to the coefficient. Okay, so all of that having been said, let's think about the application of these splines in the context of something called a general additive model. So this maintains some interpretability by additivity of terms. Okay, and this is done by using a spline for each individual variable and adding them together. So let's think about a regression like this, a linear regression that I might have, right, that we've seen plenty of times by now. I may do a slight transformation where I'm doing something like this. Where this is my smoothing function. Okay, so this is the concept of the additive model, where instead of thinking about transformations of combinations of variables, I'm actually doing transformations of individual variables and then sort of adding them up. Okay. And so what the heck does this mean? I think the easiest way to understand this is through an example. And so we're going to jump over to R and show what we're doing with these general additive models. So we're going to do a general, so GAM stands for General Additive Model. We're going to do an example of this. I'm going to be using data from that one package ISLR again. And then I need a package called MGCV, which is the thing that lets me run the GAM. So the data is hitters. Have we looked at hitters before? In the homework. Okay, yeah, great. So you guys hopefully have some sense of what this looks like. If you've done the homework already. So let me pull this up. Yeah, so I'm not a baseball guy, so these numbers don't mean all that much to me, but each row corresponds to an individual, and the columns are the baseball statistics related to that individual. So like how many at-bats they have, how many hits they have, how many home runs, and so on and so forth. Okay, so we have all this information in here, and the idea is I want to know something about the relationship between, or I should say, oh yeah, okay. I want to understand something about the relationship between the player's salary and some of their stats. Okay. And so in a linear model, I might do something like this: at bat plus, hits, let's say walks, C runs, C RBI, C walks, the division that they're in, and their putouts. And I'm going to use all of this from data hitters. right? And if I were to run, so actually, if I were to just run it like this, you'll see, even though I'm using the gam function, if I do summary gam fit, you'll actually see that this will give the exact same results as a regular old linear model. I haven't actually done anything different here. But we can actually apply splines to individual variables. Okay, and so the way that I do that is I just put an S around here. Okay, so I'm going to do that for all of my continuous variables. I'm going to turn them into splines by doing this S parentheses. I can't do it around division because that is a discrete variable, but everything else I will be able to do that. Okay, and so what does that mean? What am I actually doing here? So the way you can think about it is, in a linear model, we assume that there's some kind of straight line that goes that goes through that variable as it relates to the salary, right? But with a spline, it's kind of doing away with that assumption, and it's thinking about what's the best sort of nonlinear form that can fit through that set of data, right? And so if you were doing it with an individual single variable, let's say at bat versus salary, you'd be able to graph at bat versus salary and see what that curve looks like, right? Obviously, it gets a little bit more complicated because we're actually going across many variables, but hopefully that gives you some sense of what we're talking about here. So, okay, if I go ahead, run this, you'll see suddenly you get two sets of results, one with parametric coefficients, and so the things that I left as parametric and otherwise I did not apply a spline to, which was just one variable, the division, the discrete variable, that will give me a still regular linear beta coefficient that I can interpret, right? And so this is basically saying if you're in the Western Division, on average, you make $120,000 less per year, I think is the units. It's in thousands of dollars. Yeah, right? And so we interpret this in exactly the same way that we do with our regular linear variables. But then we have a bunch of these smoothing spline terms, right, that are over here. And okay, don't worry about all this stuff for a second. The p-values do tell us something about the statistical significance, well, which is to say whether or not, right, there is a non-zero effect relating the variable to the outcome. But we don't have any coefficients to actually describe the relationship between these two things. But we do have, conveniently, a nice visual representation of that relationship. So let's take a look at that. I can...
I have a quick question about this.
Yes.
So when I was doing homework, I removed all rows of data that were incomplete because there were quite a few, I think almost 90 rows of data where there was no data inputted for salary.
Yeah.
What does the model do with that?
Does the same thing as what you just did, which is to drop them. Because if you have no data, it can't run anything. Yeah. So, yeah, probably more proper for me to remove that explicitly so that we know what's happening, but actually running it in here will remove them for you. And I bet, so you're saying about 90 of them were
Yeah.
missing? So 322,
I'm getting on 90, I think it's like 60.
yeah. It's gotta be around here somewhere. Yeah, okay. N equals 263, so yes, 59, does that sound right? Yeah. Yeah, so, yeah, very good point. The model will do it for you. But yeah, I should be more explicit about that. Okay, so check this out. Let's do plot gam fit SE equals true, pages equals 1. No, not this stupid thing again. All right, hang on. Yes, all right.
Oh, that's cool. That's a good plot.
That's a better plot. Okay, cool. So, all right, what is going on here? So each plot represents the relationship between one of your explanatory variables and your response variables. Okay, so the y-axis on each of these represents the salary, and then the x is each variable here. Okay, so C runs, C RBI, C walks, and so on. If you guys look closely at the bottom here, these little stripes at the bottom indicate actually where the data is observed, right? And so for putouts, right, you have a bunch of observations from like 0 up to around 400, and then it gets a little bit more sparse here. And so you typically have a little bit more uncertainty where there are fewer points, right? And so here you can see in C run, same thing, very big density of points here, very few out here, and so your errors get kind of larger where there are fewer data points. Okay. So these are the spline fits of each individual variable against your salary, right? And so there are a couple sort of interesting things that are happening here, right? Which is that in some of these cases, those fits are actually not very linear, right? And so what does that mean in reference to if you were just to run this regression in like a typical linear fashion, right? One of the things that we assume about the relationship between our explanatory variables and response variables, right, is that they're linear. And so even if you're actually focused on inference and just running linear regressions, I would argue that it's probably still good practice to do this, because here we can actually observe in what instances that assumption of linearity is probably not a really good one, right? So for something like putouts, I can see a fairly straight line. Something even for CRBI, yes, it wiggles a little bit, but I would probably say that if you were running a linear regression for something like this, it's probably good enough, right? But look at, for example, at-bat and hits. Neither of those actually have are good demonstrations of linear fits, and so if you were to be running a linear regression, this assumption of the linear relationship probably isn't a very good one, right? And so, the representation of the relationship in a linear form you can show pretty directly in this sort of visual manner that you should probably be doing something different, right? And so even doing this as an exploratory method when doing linear regression, I think is probably, it's easy to do and it's probably worth it, right? And so here, I can't, again, easily say something about like a slope that relates my x's and y's, but actually, visually, I could actually tell you something about generally the expectation for what your salary might be by looking at cross ranges, and you could just like kind of plot, on the fit. Yeah.
Would it be a reasonable conclusion to make that if you look at the hits plot,
Yeah.
the reason why there's a dip in the middle is because people who have sort of a median number of hits are on the average batters or average pitchers. But if they're at 0 hits, their salary is higher because presumably they're a pitcher. At higher hits, their salary is higher because presumably they're a good batter.
Yeah, possibly. I don't know anything about baseball, so it could be the case. Is it all? So, I mean, pitchers still go up to bat, don't they?
And one league they don't. I think it's the American League. One of them the pitchers do it, and one they don't.
Wait, really?
Yeah.
Pitcher? Oh,
Yeah.
I actually did not know
Like
that.
The Mets, I think the Mets pitch, the pitchers hit, and then the Yankees they don't. Something like that. I
Is-
swear.
Isn't that like very uneven? Okay, anyways, I don't want to get into baseball, but yeah, you don't want to hear my thoughts about baseball. Okay, but anyways, yeah. So these things. Yeah. So actually, the visual examination of these things can help with deriving insights about relationships as you're actually doing right now, that you might miss in some of these simple linear approaches. Yeah, and so again, I think that even for folks who are focused on inference, it's probably worth doing things like this to investigate your functional fit assumptions. Okay. Any other questions about this? Yeah. All right. So that is wrapping up our bit on splines and their applications. And now we are going to talk about a totally non-parametric approach to some of this stuff that is very different from our splines, but can give similar types of results. Okay, so let's get into it. So we're going to talk now about the kernel regression. So this is a way to get nonlinear fits, but done through a local regression procedure as opposed to the splines that we had talked about before. And the equation for this looks something like this. All right. So the H is known as the bandwidth. And this K is our kernel function. Okay, and so what the heck are we talking about? Here's the concept. So imagine you've got some points. And let's say I were to decide on, I wanted to do a prediction right here. So at this x, what would y hat be? Okay. Okay, so help me out here. What do you guys think? Would this be a decent prediction? What about here? Or here? Or here? Or here? Right? So there's actually some information that is given to us based off of kind of what is kind of close around to you, right? So does this seem at all familiar to anyone? Does this seem similar to anything we've done before? So if you guys remember from our examples in discrete space, we talked about the KNN, right, where you're looking at your nearest neighbors. This is kind of in the same vein where, okay, I'm going to decide on a point based off of, let's say, minimizing the average distance to points within some like local area that I'm looking at. And so maybe that area is something like looking at this, right? And so that space is actually called the bandwidth, that width that we're looking at. So the kernel based on weights, and we can choose to, right, if we weigh points more heavily, if they're close, right? And so these guys out here may have less of an effect on that point than the ones that are close. But actually, if you choose to weigh everything equally, then what would happen to this point? It would actually get dragged up a little bit, right? Because yeah, it would just be the average of everything, right? And so this really is similar in concept to the KNN, right? Where if you add more neighbors, you end up just classifying based on whoever has the most points. Here, as you increase the bandwidth, you end up waiting for things that are far away as well, and so you end up averaging values, right? And so you might imagine that if I had a whole bunch of data points and my bandwidth were really big, you would end up drawing a line through the points that is equal to what? So if I were to do something like this, x and y.
Is the bandwidth a hard cutoff, or is it more like a, I don't know, standard deviation kind of thing?
It gets treated slightly differently in different contexts, and I'll show you what that means in just a second. Okay, so if my bandwidth is kind of small, right, if I were to predict at like this point here, right, that might be in between these 2 points, right? And if I were to then draw a line, I might be able to fit everything because it's looking right at points right in between. And then if my bandwidth is really big, what might my blue fit line look like?
It's much more straight, like
Yeah, what if the bandwidth includes everything?
just a straight line.
Straight line, which would be equal to what?
The average.
Yeah, the average, right? And so this is small bandwidth, and then this would be large bandwidth. And how might I choose my bandwidth?
Based on the range of data.
Maybe. Cross-validation, yes. If you're not sure what the answer is, it's cross-validation. Okay. So H is the bandwidth. The larger it is, the more we consider farther points. And then the smaller it is, the more we consider local points. So H normalizes xi minus x when big, and H magnifies xi minus x when small. So let me give a couple examples of the kernel function, because there are actually different types of kernel functions that you could actually apply. So I'm just going to give a couple of the more commonly used ones. So one is the box kernel. So this is k of x equals 1/2 if absolute value of x is less than 1, 0 otherwise. You have a Gaussian kernel. So k of x equals 1 over root 2 pi exp negative x squared over 2. And then there's the Aponishkov, I don't actually know how to pronounce it, kernel. So this is k of x is equal to 3/4, 1, oh, let me write that better. 3/4, 1 minus x squared if absolute value of x less than or equal to 1, 0 otherwise. So the kernel function here, so that's really referring to the value that you derive out of this thing, right? And so so going back to Christopher, your question, the choice of the kernel function plays a role in the way that the choice of the bandwidth like weights the values that you decide to, or that the regression ends up choosing in slightly different ways, right? And so in like a Gaussian kernel, it thinks about the it thinks about it in a way that's kind of like replicating a normal distribution and the value of the point based on the bandwidth that's chosen. So you guys can play around with the kernels. We're going to look at some examples of applying the kernels, and you can see, depending on the choice of your function, the way that the kernel like converges to a particular fit will differ between if you're using like a box or a Gaussian or a Ponitkov. But in practice, I think probably the choice of your bandwidth is probably the most important thing in being able to get like a good sort of functional form. I would say for most problems, you're probably going to be able to get similar convergence with different kernel functions.
Xi minus x is sort of the distance of every other point from where you're looking at them from, like that dotted line you drew in the graph above, and h sort of scales that distance before you throw it into this
Yes.
distributions, basically.
Exactly. Yep.
Okay, and that's why some of them are explicitly different if x is less than 1. No, wait, that'd be if h is less than 1.
Sorry.
It's okay.
So let me. Yeah. So the xi minus x over h, it will care about that's what ends up in your sort of x term here, but it's a little bit hard to visualize because you're also dividing by this whole this whole piece. But generally, the thing that happens is that it will have a weight assigned to multiply against your yi that depends on both the kernel function and then how far your xi is from each individual x point. Okay. So let's do this with the same example that we did from last class. So kernel example. I'm going to do this whole thingamabob again. Oh, hang on. All right. So you remember this thing from last time. The points will be a little bit different, right? Because this is drawing from a random distribution, but overall the shape looks like this. Okay. And we already looked at what this looks like. If you just do a linear model connected to it, So let's do a kernel model. So we're going to use a library called NP, which I believe is a non-parametric, or NP stands for non-parametric. Yeah, non-parametric kernel methods. So I have to do a little bit of bookkeeping. We're going to have so I'm doing x.ord, which is ordering my x's. And so thinking about what a kernel regression is doing, why might I want to order my x's?
You mean sort them?
Yes, going from smallest to largest, right? So a kernel regression fundamentally is a local regression, so it wants to look at slices of the data, right, based on your bandwidth. And so it's most efficient to sort all of that data first. Okay. Or, okay, wait. That's what happens behind the scenes, but actually I'm going to be using this for the plotting purposes. So ignore what I just said. It actually does do the ordering, but it's smart enough to do it on its own. It doesn't need you to do it manually. Yeah, okay, so forget what I just said. Yes?
I was wondering, due to the nature of how it is calculated, are there like problems close to like the borders of the data? Because then in one direction you have less data points. Or is that
No, it doesn't really matter because it's all based off of thinking about things relative to the bandwidth anyways. So imagine that, so the error does become larger in places with sparse data points, right?
Yeah.
But you can imagine that there's a data set that has like maybe less dense points somewhere in here. It doesn't even have to be at the ends, it could be in the middle, right?
Yeah.
And in that case, it would still be able to handle the, like running the local regression, but the error bands in the area where there's lower density of points would be larger.
Yeah.
Yeah. Okay. So we're gonna do this, and actually I'm gonna do color equals gray. Okay. So kernel model 1, we use a function called mpreg, and we're going to do y regress on x as usual, and BWS is the size of the bandwidth. Okay, so I can run this. So we're like very solidly in the completely non-parametric realm now, and so there's literally nothing, there's nothing that you can really interpret, right, that we're trying to make inferences on. Like even with the splines, there are actually coefficients associated with the basis functions, which are nonsense, but here, really, we don't have the ability to say anything. It will still give us metrics for the overall model, right? So we have things about like the R squared and the standard error that you can extract, but nothing interpretable in terms of relationships between your x's and y's. Okay, so I'm going to plot the true function and then I'm going to plot our fit. Okay, so here is the data. Oh, cosine, not cost. That red line represents what we know to be the true function that generated these data points. It's not ordinarily something you would have access to, right? You would normally just have the data. And let's take a look at how well our kernel regression does at creating a fit from the data that's observed, and we can see how close it is to the true function. I'll also note that I believe I didn't specify anything about the kernel function, and I believe the default one is the box kernel, but I might be wrong about that. Actually, let me.
It looks like it says second over Gaussian.
Okay. Yes, you're right. So it's the default is the Gaussian kernel. Sorry. They're very common to use, and the performance is pretty similar. Okay, so here, the blue line is what we're getting out of the kernel, and you can see, I think it does generally a pretty good job at kind of replicating our true function. Okay. It's overlapping for the most part, and it's, I guess, getting hung up a little bit at each of the peaks and troughs. Okay, so I'm going to copy and paste a whole bunch of other stuff. It's exactly the same thing, but all I'm doing is actually just changing the bandwidths, okay? So kernel model 1, we use a bandwidth of 0.05. Kernel model 2, everything is exactly the same, except that I'm using a bandwidth of 0.01. So when I use a smaller bandwidth, what happens? Sorry? Oh, yeah, so possibly overfitting. So let's take a look at what happens here. Oh, okay, hang on. Let me change all of my points to gray. All right. Okay, here we go. And here's the one with a slightly smaller bandwidth. And you can see that it already here, it's starting to oscillate a little bit more. So here you might, right, so this is a point at which you might suspect overfitting, right? And really what's happening is as the bandwidth gets smaller and smaller, it starts to favor points that more heavily favor the points that are, within that narrow band, and it will start to try and essentially almost like connect the dots, right? And you can see that even more clearly. I'm going to change the bandwidth to be even smaller, so 10 times smaller than that. And here you get to a point where you're small enough where you're almost, right, sort of connecting point by point. It's not quite happening in this case, but you can see, right, this might be something that we would describe as really sort of overfitting. And let's go in the other direction. Now let's see what happens as you move the bandwidth larger and larger. Okay, and so it's starting to even have more difficulty with some of these peaks, right? Because what ends up happening is the bandwidth is large enough where it's sort of averaging out the large values up here and smaller values down here, and so that's going to bring your peaks and your valleys kind of closer, right? So effectively, what you're doing, it's almost like in the smoothing spline, you are keeping it from being able to rapidly sort of change directions to accommodate how points are distributed. Let's go even bigger with the bandwidth. And you can see at a certain point, right, it's thinking about such a large sort of conglomeration of points that it's really smoothed out any of the sort of variation that's there in the data, and even larger. At a certain point, it just becomes flat, and this value here is going to be equal to the average value of all of the average y value of all the points in your data. Okay? Any questions? Yeah.
Yeah. We know there are many kinds of the kernel regression, for example, the Gaussian box. So how do you choose that?
Yeah. So, in a practical sense, you typically, so it to some degree has to do with the way that the data is distributed, but oftentimes you're kind of making these trade-offs in the way that it converges and the sort of like computational performance of these things. Sometimes the convergence can be different when you're using different sort of kernel functions. But as far as like practical advice on which ones to pick, I would probably stick to, these three to begin with. And then if there's a particularly compelling reason that may be related to like the computational complexity or the way that it's converging, then you might check with other kernels. But yeah, I mean, I don't do that much local regression stuff with kernels, and so yeah, I don't know if I can give much more practical advice beyond that, but okay, any other questions? Yes.
I guess not necessarily the question, but I used Gaussian kernel, kernel estimation in a project last quarter.
Yeah.
I wasn't at the point yet where I was evaluating the different fits on like R squared, but just on visual inspection, the Gaussian kernel seemed to match like the histograms that I generated of the data the closest.
Yeah.
But then I wasn't trying to fit across an actual range of data. I was fitting a distribution.
Yeah.
So I'm not sure if that's a good use of it.
Yeah, don't know. I guess I would need to know more context about your problem, but okay, really quickly, the last thing I'll show with this is yeah, what's the best what is the best bandwidth that you could use? Well, we can take our cross-validation function that I know you guys are all pretty familiar with at this point. I can kind of replicate that for specifically kernel regression. And if I apply that here, I can test, so on line 75, I can test a whole bunch of different bandwidth sizes, and then kind of pick the best one. So let's see here. Based on like an out of sample mean squared error. Don't remember what this spits out here. Okay, yeah, across a whole range of these. And if you look at the average lowest of the mean squared errors, I think it's ends up being this one, 0.025. And so if I run that, oh, okay. Yeah, so here I can end up finding kind of my best bandwidth size to fit to this, and it'll end up looking something like this. And actually you can see maybe you get a little bit of overfitting here, but the problem that I pointed out with the very first plot about the peaks and troughs not lining up, this one does a slightly better job, right? And so in this case, yeah, this particular bandwidth choice of 0.025, which we arrived at by doing our regular cross-validation stuff, ends up giving us this fit. Okay. Okay, so let's take a quick break, 5 minutes, and then we'll come back and start a topic on time series. Or one more thing on splines versus kernels, and then time series.
Very busy weekend.
Question.
Yeah, what's
about
up?
Kernel regression.
Sure.
In kernel regression, if my y data is, not normal distributed, it's a quite, not the normal regression, it's not normal distribution, is that will be impact on the kernel regression prediction?
No, not really. So
I don't need to, to log transfer or something, transfer to the normal regression, no.
no, I think you're talking about the functional form of the relationship, not the distribution of the data. But either way, it doesn't matter, because with the local regression, it doesn't care about any of that stuff.
Okay.
That's why it's so powerful.
Okay.
Yeah.
Okay. One more question about the x. Your example is just one, x in here.
Yes.
If I have multiple x and the different x can have the different, maybe need the different bandwidth. So does this, function in R? I can, have different sighting for the different x.
So usually the usually the data is normalized and then or scaled, and then the bandwidth applies equally in every direction. You can have different bandwidths for different variables,
Okay.
but it's often easier to normalize it and then just apply a single bandwidth.
Okay.
Otherwise, you have too many degrees of freedom. You can change many combinations of bandwidths, and then it becomes a computationally difficult problem.
Okay.
So yeah, usually you try and normalize the data or scale the data, and then have the bandwidth apply across many dimensions.
Yeah.
Yeah.
But the reason why I would like to ask this question is, my research is trying to do to study one stream water contamination factor.
Okay.
And based on the common knowledge, we know this stream pollution factor will impact by the season,
Okay.
by the discharge, and by the time.
Yeah.
Yes. So we know the season and time, the time window
Yeah.
is different.
Yeah.
And also the discharge is, the time window is different. So as you mentioned, should I to normalize them and use the one time range? I mentioned time range actually is you said the bandwidth, right? What I understand.
Yeah, well, so you would normalize them and then you would run the regression on multiple variables but have a single bandwidth, right? And because they're normalized, it's okay for the bandwidth to transfer across dimensions.
Okay.
Yeah.
Okay. Okay. I will try that.
Yeah.
Try that again. Thank you.
Uh-huh.
I was so over social.
Hi.
So I'm working on notes,
Okay.
and I am trying to. So what I essentially did was I went back into our notes, and I looked at the formula we previously used. I think it's in 7. Yeah. So in 7, this one was a forward, so we would add
Yeah.
each one. And what I was trying to do was I was trying to think, okay, I want to remove one, and then paste them together.
Yeah.
But
So
I don't
okay,
think
let's
it's
let me
listed.
let's talk about this after class.
After class.
Yeah.
Okay, great. Thank you.
Uh-huh. All right. So last thing here, we're going to talk about, from a practical perspective, splines versus kernels. So splines have better computational speed. Maybe I'll put a plus. Simplicity, I think, is a little bit easier, right? We could just apply the spline to the variable. And then there is, to some degree, right, some clarity of controlling the curve directly. Right, and so you apply a basis function to a variable that controls the entire span of the curve, right? And you can have specific parameters that affect the fit of that curve, right, via things like knots, right? With kernels, these are typically easier to program. You don't need to make a specific decision about fitting or about choosing specific variables to apply splines to, right? This, you just throw it all in, and then it just does this like local regression stuff, right? Easier to analyze mathematically. And then this is easier to extend to multiple variables. So we didn't really get into thinking about multiple variables. With splines, we kept them as independent, but you can imagine that you could fit some kind of like spline contour to multiple variables. Mathematically, it starts to become pretty tough because now you're thinking about the application of splines into like multiple dimensions, whereas with kernels, it's just this like local regression thing, right? And so the consideration for the space in which the regression is being applied to, there's like a very mathematically rigorous way of just figuring out what the next point is, right, through your box or Gaussian kernel or whatever. And so, yeah, it's actually quite a bit easier to think about kernels in multiple dimensions than splines. And kernels, so combos of continuous / discrete is easier to deal with. So these are like some considerations for trade-offs between splines and kernel regressions. Yeah, that you guys might think about when faced with a choice of deciding which regression approach to take. All right. So that concludes that piece. Yes.
Out of curiosity, does the kernel regression have something to do with how you can allow the Jupyter notebook says kernel
Maybe. If you're talking about, so I don't know the exact context in which that appears. If you're talking about like kernels and programming, that's different. But in data analysis, yeah, kernel, like a kernel approach is a pretty specific type of thing that happens.
I
Yeah.
was thinking of a type of memory.
No, that's different. Yeah, yeah, different concept. Yeah. Okay. How much of this can I get through today? Okay, so the next thing that I want to talk about, this is like kind of a poll through the years of topics that people were interested in, and so this is kind of becoming a more permanent addition here, but maybe slight departure from directly talking about these semi-parametric, non-parametric approaches. So time series. Is a popular topic. And so this is a common but special case of statistical modeling. The obvious correlation introduced by sampling points adjacent in time so this can restrict the applicability of many conventional statistical methods. Okay, and so probably the most common issue that we think about here is that in your typical like regression setting, we talk about sort of independence of your explanatory variables, right? And so if things become heavily correlated, then you have issues like multicollinearity, which can be problematic for interpreting relationships between variables because they're kind of like muddling the effects of one another. And there are a series of other sort of things that there are a series of other sort of assumptions that we make about the way that models operate, you know, besides this sort of independence of the explanatory variables, which become problematic when we're thinking about time series, right? And so this is a lot of the specific techniques regarding time series has to do with the fact that you have these common issues sort of interrupting the types of assumptions that you would make in simpler models and kind of dealing with that, right? So let's talk about a classic regression for time series. So this might be something like y of t is beta 0 plus beta 1 xt1 plus beta 2 xt2 and so on. Okay, so let's think about something that looks like this. So t oops. So in time period 1, 2, 3, we may have observations, something like A, B, C, D, E, F. So obviously the x's relate to the y's, right? That's the whole point of setting up our model like so. But you may have things where the previous time period may have some kind of effect on the next time period. So so D may have some influence on E. But then you may have this kind of circular thing happening where you have this issue where your y's may actually be related to your x's such that x's in the present may be influenced by your y's in the past. So then I may observe something like this, right? And if that is the case, then you would expect that this sort of trend would kind of continue in terms of those relationships over time. And so I would again see something like this happening, okay? And so we can represent this in the model here, right, with what are known as lag variables. And so this might be something like yt is equal to beta 0 plus beta 1 xt1 plus I can actually simultaneously capture all of those effects by adding in, let's say, alpha y t minus 1, right? Because y t minus 1 is equal to beta, or let's use a different thing. Delta 0, or wait, gamma xt minus 1, or t1 minus 1. Right, and this whole term could actually substitute into here. Or I should say, this whole thing can sub into here. Okay? So you have this ability to add in these lag variables to capture these effects. Okay, so let's do an example of this. So example time series data creation. So we'll have something like time 1 to 100, x1, cumulative sum of r norm 100, x2, cumulative sum r norm 100. Oop. And let's do y is 0.5 times x1 minus 0.3 times x2 plus r norm 100. So this is a linear function of x1 and x2. So if I plot all of this together, it might look something like this. Okay, what's going on? Oh, I did not run this. Okay. So it turns out that when I run a regression, one of the critical concepts as it relates to time series analysis is that statistical properties of some of the approaches that I use get disrupted because of the inherent relationship between variables over time. And so statistical properties of like your mean and variance staying constant, which is necessary for many modeling assumptions, gets violated. And so there's an important concept called stationarity. So let me see here. Yeah, actually, let me jump back to the notes really quick. Before we continue on this particular example. Stationarity is a critical concept for time series analysis. Because it ensures statistical properties such as mean and variance stay constant. Okay, so I'll give an example of this. If you have something like time and stock prices. Maybe you have a plot that looks like this, and you have this upwards trend. So if you were to do this in a traditional setting, so your model might predict continuously increasing prices even when conditions differ. Right? And so think of it this way. You have a particular event that happens at a specific time here. And let's say you observe that event happening for a small period of time. And then you observe kind of a similar event happening, right? So let's say normally we could, even if you could perfectly correlate this particular event as happening during a downturn in stock prices, because of the upward trend, it would actually predict something like a positive increase in the stock price because of this upward trend that's happening over time. And so if I wanted to isolate that effect, I would want to be able to control for stationarity in order to be able to like isolate that. And that actually means transforming the data in a certain way. And so there's a question, why can't I just add variables to control for these upward trends, or trends in general, that might be correlated to time? So one, you never fix this issue. So many models require stable means / variances to operate properly. It can lead to unstable models over time, lowering predictive power, and then risks multi-collinearity and overfitting. And sometimes including all of the variables that might be connected to time trends might just be like not practical, right? Because there could be a lot of too many variables to try and control for, or things that are kind of unobservable, right? That maybe you don't even necessarily need to care about. Okay. So how can we deal with this? We're going to talk about a couple of different ways that kind of either address stationarity or get around it in certain ways. So one way to address and get stationarity is known as differencing in time series. So the first diff might be delta yt is equal to yt minus yt minus 1. And you can do the same thing with the x. Xt is equal to xt minus xt minus 1. And you would do same for every variable. And then second diff, you can continue doing the exact same thing. So it can continue differencing if non-stationarity is still present. Yes.
Did you, I guess, directly explain what stationarity was? You said it was a critical concept, but I'm not sure what it means.
Yeah, so basically, stationarity is when you remove trends that are happening over time. So that might be, so for this particular example, it's possible that applying stationarity would isolate the effect, or it would isolate the ups and downs in the stock market prices from the overall upward trend that you would observe over time. Yeah.
How do we statistically measure the non-stationary?
Yes, so there are a number of statistical tests that you can apply. Actually, do I have them in here? Well, I can't look at my screen. I think I will show some examples of that in R. I think. We'll see in just a second. Any other questions? Yes.
When you want to analyze time series or something like this, do we need to consider outlier, for example, do we need to identify and to remove those outlier now?
So I would say that the way that you would do this is first to make the data stationary, and then you can consider the outliers. And then the whole question of whether or not the outlier should be included goes back to my lecture on outliers, on kind of how that changes your assumptions, what the removing the outliers actually does to the underlying data, and whether that's like appropriate, right? And so that's kind of left up to you. But generally, you would try and make the data stationary first before dealing with the outliers. Yeah. Okay. And so what ends up happening is you have delta yt equals something like this, plus beta 1 delta x1 t plus beta 2 delta x2 t plus beta n delta xn t plus epsilon t, right? And so this beta is the change in response to a unit change in x as opposed to absolute levels. right? Because you've differenced out the trends that are happening over time. So let's show this in R. Okay, so this particular data set, I can difference the data. Okay. So I'm using this function called diff, and then I put in a vector, right? And so in the original data frame, which is, let's do this, view TS data. Oh, did I not? Oh, sorry, I omitted one line where I just put them all into a data frame. So TS data, data frame, T equals time, Y equals Y, X1 equals X1, X2 equals X2. Okay, so if I do a view of this, right, I have 3 columns, T, my Y, my X1, and my X2. Okay. So I want to add a set of columns that difference so I want to add 3 columns. One column that's going to be delta y, which is each value of y minus the previous one, and then a delta x1, which is the same thing, each value of x1 minus the previous one, and then a delta x2, same thing, right? If I apply that difference function, how many, so there's 100 rows, right? When I do difference, how many points do I generate? 99, right? Because the first one has nothing to subtract against, right? And so you'll actually note that in this differences piece, so when I create this column called diff y, which is the delta y I was talking about, at the front I put an NA because you have no value to difference against, and so that'll help. That allows you to put it into the data frame, which has 100 rows, when your thing is only 99 long. Right. Okay. So we'll do this. We'll do this as well. And x2. So the differences equals 1 is one of the input options on the diff function, which just means that I'm subtracting the one entry previous. You can have it do kind of larger intervals by changing that value if you wanted. Okay, and so once I've run all those guys, if I go up to view, you guys can see here, right, so I have NA at the beginning, and then diff y, so the second row is equal to 0.835 minus negative 403, right, which end up being plus, so that should be 1.238. Yeah, and that's what we see there. Okay? So let's actually graph those plots. So these ones are the ones that are not differenced and do not have stationarity. And we're going to see how that compares. I'm just going to copy and paste this. I'm going to get rid of the NA row, so now it's just going to be 99. Okay. And so now I have forced the data to be stationary, and now I'm able to apply my regression models. So here, we can now run a regression model. Let's do the diff model. So this is, oops. This is regression model on differenced data. So diff model, LM, diff y regressed on diff x1 plus diff x2, data, TS data, summary, diff model. Okay, so let's take a look here at our estimates. So this tells us, right, from the stationary data, the relationship of the change in x relative to the change in y looks something like 0.6, and the change in x2, if you change that value, would relate to a delta y change of negative 0.5-ish. Okay. And so doing it this way lets us get around these issues of having stable means and variances when we're running the regression. Yeah. Okay. Any questions on that? And actually, we can do a quick comparison of if we do the non-diff model, or maybe let me do. If I were to just run y on x1 plus x2, yeah, you'll notice that the values are, hold on, let me see here. Yeah, you'll see that the values are going to be pretty different from the originals, or from the ones that are difference, where you actually have the stable mean and variance. Okay, so that is one way that you can address that particular issue. Any questions? Okay, so we can fit in one more technique here. Okay, and that is moving averages in time series. So this is an alternative way of addressing stationarity, where we focus on smoothing things out in order to reveal underlying trends. So it's a little bit different in approach because differencing focuses on removing trends or cyclical components, whereas moving averages tries to smooth them out. So the rough algorithm for how this works is we choose a window size. So this is like our K period. Apply moving average, MA, for each variable. So this looks something like this. And then we can fit a regression model. So MA Y T, so this is equal to beta 0 plus beta 1, MAT X1 plus beta 2, MAT X2 plus dot dot dot, beta N, MA T xn plus epsilon t. So it's pretty similar in approach, except instead of doing the delta here, where we difference the time from before, we have MAT, which is taking the moving average at a particular time, where you're looking at some kind of window, which will smooth out like x's over time and y's. Yeah.
But technically, it has like data for like 10 years for like a bunch of different regions, just like average use 10 years as a time frame, average everything, and then I have maybe different variable, then I can see that.
Yeah. So we're gonna do that with this data set right here. Let's see. So I'm gonna copy and paste from above this exact same thing for a moving average example. Time from 1 to 100, cumulative sum from a normal distribution, and then the same function as before. And I'm just gonna create a new data frame called MA data. And then it's, I think, exactly what you're saying. So we're gonna use a library called FPP. Let me run all this stuff again. To help do this procedure. So to do a moving average calculation, first I want my window size. Here I'm gonna do a window of 5. So it's gonna look at 5 years in either direction, or it'll do 2 years in either direction, so that I have a total of 5 years. So 2 years in front, 2 years in back. You can also shift the way that the window looks. If you're only looking in one direction or the other, and that option is with this thing called sides. But okay, so weights rep 1 over n. So that's actually just how you do the average, because it's gonna, this function just does the sum by default. So filter is the function that we're talking about. MA data $y, weights, sides equals 2. And I'm going to do the same thing for x1 and x2. So here, x1 and x2. Okay, and when I view MA data, not MAD data, MA data. Right, we have MAs for the first two rows of the moving average. And why is that? Yeah, exactly. There's nothing to take an average of on the first one going 2 steps back, right? So this is a window of 5 with 2 in each direction, including myself, right? And so if I'm in position 1, there's no data in row 0 and row -1, right? So you start with enough here, and so that first moving average y is equal to the average of the first 5 rows in, of y. So the first 5 rows of this, if you add all this up and divide by 5, you'll get that value. Okay? Then I can drop the data with NA omit, MA.data. Oh, what did I just do? Okay. And I can plot this data as well, just so you guys can see what that looks like. So here, it's been smoothed out, so it ends up just looking like this trend line. And when you do regression, so regression model on moving averages. It doesn't always look this smooth, but that is a feature of moving averages, right? As I was saying, it tries to smooth things out. Let's see what happens. So here, in this particular case, these moving averages get us quite close, right, to our original true function, right, which is the, I think, 0.5 times x1 and negative 0.3 times x2. Okay. Okay, we don't have time to talk about autoregressive models, but that's all right. Yeah, I'll leave you guys with this. So two common sort of techniques in time series analysis that let us kind of get around some of the fundamental issues related to variables being sort of correlated with themselves over time. Okay, so there we have it.